Right. Yeah, thanks a lot, and I'm happy to see that so many of you made it across to this room. Yes, my name is Mats Granath. I'm an associate professor at the physics department at the University of Gothenburg. I'm also involved in the Wallenberg Centre for Quantum Technology, which is hosted by Chalmers. It's a quite big project, a 1 billion kronor project over 10 years with the ambition to build a Swedish quantum computer. A small part of that, I work on quantum error correction and some parts related to quantum machine learning. So what I will talk about today is quantum machine learning. Basically, I want to look at sort of the interface of machine learning and quantum computing, how those can influence each other. So sort of the title reflects two perspectives on this. So quantum machine learning, I think, is what one would typically think of. So we perhaps want to use a quantum computer in some way to facilitate doing the traditional machine learning or deep learning types of problems where you look at some classical data and you may want to classify that or things like that. That, as I will point out, there's no clear path to that, but there are some ideas, and I will point to some of that. The other path, which is in a way more straightforward and not maybe as exciting, is to use machine learning for quantum or for quantum computing. So there's lots of work of that, and I will mention some of that too. Right, so the outline of my talk is the following. So I have a few slides introducing some basics of quantum computing and what's going on at the moment. So then I will talk about quantum machine learning. What is it? What can it be? And these different types of talking about or combining machine learning and quantum computing. I will bring up a focus point to one particular example of quantum machine learning, which is to use a quantum circuit as a feature map generator. So basically, if you think of a neural network, let's say, except for the output layer in the neural network, the first part you may think of as a feature map or a generator and embedding into some space, and then the last layer is like perhaps a linear classifier, and then one can use a quantum circuit instead for that. Right, and then some of the machine learning for quantum, and finally conclude. Right, okay. Maybe this is not the last version of my slides. I think I had some transitions in this, but yeah, that's good enough. So quantum computing. So one of the first people who talked about this was Richard Feynman. He's one of the great physicists of the 20th century. He was the founder of, or inventor perhaps, of quantum electrodynamics, describing the interactions between light and matter. So he said, he's famous for this quote, nature isn't classical, damn it. If you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. And it's actually turned out to be pretty hard. Actually, what he's describing is perhaps not what one would call a quantum computer these days. It's more like a quantum simulator, and it's actually not exactly the same thing. But I will focus on quantum computing, which is actually making a computing machine with quantum bits. Yeah, so here on the left is, those of you who have some physics background, you know this as the Bloch sphere, describing the state of a single qubit. So instead of the 0, and those look pretty bad actually, I didn't see that. What happened with that? So instead of the 0 and 1 of your digital computer, you now have states which may be a superposition of 0 and 1. So like the cat state, Schrödinger's cat, which can be both alive and dead at the same time, and actually some arbitrary complex linear superposition of alive and dead. No, okay. Yeah. So this is going back a couple of iterations on my talk, actually, these slides I noticed. Okay, yeah, and so another thing with the quantum computer which is fundamentally different from a classical or digital computer, is entanglement. So you can have these non-classical states or Bell states. So like a 0, 0 plus 1, 1, which means, importantly, if you measure, let's say, the first qubit there, and you measure a 0, then you know that the second qubit has to be a 0. And if you measure a 1, the second qubit is a 1. That's not going to happen in a classical computer. You cannot write that as a product of single states. Yes, I forget that I'm on an early version. I also want to mention interference, which is a very important aspect to a quantum computer, which is maybe the most important aspect, actually, which is not on here. So that's something that's used, for instance, in quantum Fourier transform, that you can interfere between bit strings, so that some bit strings get enhanced and some get cancelled, and that's something that's used in Shor's algorithm, which is the basis of that to factorize large numbers. Okay, so something about programmable quantum computer then, which is what we want to build here. So then the quantum code actually corresponds to a quantum circuit. So here's an example of that to create a Bell state. So starting with 2 qubits in the 0 state, you act with 2 gates. So in that sense, it's works in the same way as a classical computer. You have these gates, but they are now quantum gates. So the first one there is called a Hadamard gate. So that creates a superposition. So we can think of that as a superposition gate. Your state on the first qubit is now 0 plus 1. And then you have a C0 gate, which, if the first qubit state is 1, it flips the state of the other qubit. So then after that you've created this entangled state. So in fact, a small set of such gates gives what's called a universal quantum computer. You can do everything, including any classical, any computation you can do on your digital computer, you can do on a quantum computer. It's just going to be very slow, so you're not going to want to use your quantum computer for that purpose. So actually, to make use of the potential power of a quantum computer, you really need special algorithms. So I mentioned Shor's algorithm. There is a number of related linear algebra subroutines or algorithms that one can use. There are things called the quantum approximate optimization for optimization problems, and quantum variational eigensolver is something that people explore using in quantum chemistry. Yeah, so one thing you need is special algorithms, but even then, it's the next problem is that it's actually very hard to construct fault-tolerant qubits and gates. The qubits are very sensitive to noise. So here is an example. If you now want to make it error corrected in order to factorize this 2048-bit integer in 8 hours, you may need 20 million noisy qubits. So that's combining these noisy qubits into some more robust qubits that you can use for your logic. Yeah, and you need a lot of them, and the largest quantum computers today have around 100. Yeah, it's a long way to go, but in fact, there has been these experiments by Google Quantum AI showing that there's something a quantum computer can do that a classical computer cannot do. So it's these quantum supremacy experiments. Basically, the setup of this is that you have your quantum computer on 30, 40, or 50 qubits, and you run a random, basically, a pseudo-random circuit on that, and try to calculate the output of that, what's the state that comes out, is actually a very hard problem classically. And so they show that if you make this big enough, the quantum computer can do it, but the classical computer cannot, even if you use the largest supercomputers. What the quantum computer is actually doing is basically just simulating itself. So it's not, I mean, it's sort of inert to the quantum computer. But as a proof of principle, it's something, but it's not very useful. So, yeah, this meme sort of puts it in context, maybe. But despite that, the long way to go, there's a huge boom right now in quantum computing. So I was at the APS, the American Physical Society March meeting in Chicago 2 or 3 weeks ago. And there were, I don't know, 5 or 10 parallel sessions on things related to quantum computing. And all of the big companies were there, and a bunch of smaller startups that don't seem to have any problems attracting investments. I mentioned WACQT again. There are lots of other big efforts going on at other major universities as well. So it's a very exciting area in that sense. Here's another display of that, showing also that there are many different technologies being developed. So I think on the top left there is what people here at Chalmers are working on, and also Google and several other of the main players working on superconducting qubits. I mean, that has some advantages, but it's also not clear how to actually scale it up to make very many qubits and connect those. You also need to have things at extremely low temperatures, which is a problem. So then there are these optical quantum computers that a group, Xanadu, for instance, working on. And those one can keep most of the operations at room temperature. On the other hand, it's very hard to interact, to get light to interact with each other. So, yeah. So let's see now. Yeah, so now I probably spent maybe most of my talk introducing quantum computing. So now let me get to quantum machine learning. So one way to think about quantum machine learning, one can divide it sort of into these 4 categories. So think about what type of data one has. Is the data classical? So with classical data would mean pictures of cats and dogs, perhaps. Quantum data would be more native to some quantum process, maybe already represented in a form which is suitable to put in your quantum computer. Or it could be that you look at a quantum system. And then the type of algorithms are the classical or quantum. So the CC up there to the left is what we would talk about as machine learning most of the day here, except in this particular talk, I think. So the CQ then would be what most people would think of as quantum machine learning. So looking at classical data, but somehow using a quantum computer to address that. So let me, as I said in the introduction, I will bring up one specific example of quantum machine learning. Oh yeah, I had, oh, right, never mind that. So think of a deep neural network and look at the first part of it, the input layer and the hidden layers. And perhaps we have a problem here where we want to classify airplanes and cars. Let's make it simple, just have 2 categories. And then that first part of the neural network does some sort of nonlinear mapping into some higher or lower dimensional space. I guess in this case, actually, the input space is pretty high dimensional. A number of pixels times a number of colors, right? And then maybe you reduce that to some lower dimensional representation in the final hidden layer. The point of that whole mapping is, of course, in that embedding space, you want these data points to be separated, such that your output layer can very easily distinguish between these different types. So by just drawing a decision boundary in that space. So the last layer acts as a linear classifier or a support vector machine, for those of you who know about that. Actually, a quantum circuit can then be thought of in a similar way as a quantum embedding. And the interesting thing about it, as we mentioned earlier, looking at the Google experiment, is that it's actually an intractable problem for a classical computer to understand what's going on if you use a quantum circuit as an embedding, at least if you make it large enough. So even though we may not necessarily know or understand if it will be useful or not, at least we don't know that it wouldn't be useful. So here's an example of a recent paper, which I think is very nice, where they also the resolution is, I'm sorry, apologize for the bad resolution. So this is of course a ridiculously simple problem they're addressing here. The original data is just 1D data, and in plus or minus 1, red or blue, and we want to use quantum embedding to classify those. And of course, for us, it's completely trivial, right? We could have just taken perhaps the absolute value, and then we would be done, and we could easily do a linear classification, drawing a line between red and blue. So the way it's set up then is that you have a number of, so it's just a single qubit in this case, and you have a number of quantum gates which do rotations on this block sphere, rotations based on the value of the data, so this x1 coordinate, and there are also some trainable parameters. So like in a neural network, you have trainable weights now in your quantum circuit to produce this quantum embedding. And actually the nice thing, well, so there are both nice and problematic things about this. The nice thing is you can calculate gradients to optimize your quantum circuit. The not so nice thing is that you cannot really do backpropagation, because there is this thing called the no cloning theorem, so you cannot make copies of your state in quantum mechanics. So it means that in order to train sort of a quantum neural network, if we would call this a quantum neural network, you do need to make many more. You basically need to do one operation per gradient on your parameters. Whereas, you know, in deep learning, you have backpropagation. You don't need to calculate all the combinations of gradients all over again, right? You can use your earlier gradients. So it takes. So in that respect, it's heavier to train a quantum neural network. There is an additional problem, and that is that you actually need to do lots of measurements as well, because you need to measure the state of your circuit many times to get good statistics, because it's all probabilistic here, right? But as an idea, I think it's pretty nice. And so here below is another version of that, where they combine a ResNet with a 2-qubit quantum circuit to classify ants and bees, I think. Of course, most of the heavy lifting is actually done in the classical neural network there. But I think it's a nice, as a point of principle. And as I said, we don't know what's going to happen if you scale this up. The problem is that they cannot actually, it's really hard to simulate classically. So going to more than 2, up to 10 or 20 qubits, well, you might be able to go up to 20, but beyond that, you cannot really do the classical simulations anymore. Yeah, so we don't know how this will work, if it has some advantages. Okay. Oh yeah, so here I just mentioned some work that we have done, which is related. So this is work by industrial PhD student David Fitschek, who is at WACQT and at Volvo. So we wanted to look at something called the heterogeneous vehicle routing problem, which is sort of related to the traveling salesperson problem. You want to optimize some routes. In this case, you want to deliver goods to customers in a most cost-efficient way. And so you have a fleet of trucks that can carry different amounts. And we managed on the quantum, or actually not actually running things on a quantum, but simulating a quantum computer, we managed to optimize this type of problem with 2 trucks delivering goods to 3 cities. So these things are all sort of point of principle. We're not going to use a quantum computer for these types of problem anytime very soon, I think. So how about this? Well, so if we think about the connection between machine learning and quantum computing, maybe going the other way will be more important in the near term. So here I talk about machine learning for quantum. So I'm focusing in particular on quantum computing. One can use machine learning for lots of different quantum problems, and people do that these days. Just show an example of that here. So here I show a quantum circuit. If you have an algorithm, quantum algorithm, you formulate it as a quantum circuit. Typically, that quantum circuit that you want to run has gates between all your qubits. As it turns out, when you build a quantum computer, the hardware will not allow you to make gates between all your qubits. It's typically situated on some grid, and you can only interact with the nearest neighbor qubits. So actually, it is a difficult optimization problem of how to actually transform that ideal quantum circuit to an actual quantum circuit that you can run on your quantum computer. So that's something called quantum circuit optimization. And so for that, in this example, I show how people have used deep reinforcement learning to try to address that problem, to make the circuit that you can run it on whatever architecture you have on your quantum computer, and you also want to make it as short as possible, because the gates are noisy. You want to use as few gates as possible. Another example, this is from my own work. We have looked at using, again, deep reinforcement learning for quantum error correction in this case. So quantum error correction is the idea of how to use your physical qubits that are noisy, as I said, or sensitive to noise. If you combine many of them in something called a topological code, so you basically make an entangled state of all those qubits. So to the left here shows, all those circuits are physical qubits. And combining, let's say I think there are 49 of them here, or maybe there are 81. If you combine them into one entangled state, then that would represent one logical qubit, which would be more robust to noise. So that's the way to go to do quantum error correction. And the problem is you still need to correct this, because if you let errors accumulate, eventually also that logical qubit will go bad. The nice thing about this, and I've had several master thesis projects and bachelor thesis projects. I don't know, I saw maybe some of my former students here in the audience. The nice thing about this problem is it can actually be formulated sort of like a game, right? I don't know, playing Go or something like that. So it's very nice for playing around with machine learning and reinforcement learning. Okay, I think I'm to my conclusions. So I would say quantum machine learning is certainly in its infancy. There are 2 reasons for that. Quantum computers are very primitive. algorithms are largely unknown as well. So I think the verdict is still out on when and if quantum computers will be useful for machine learning. I think there is hope, since we don't know that it will not be useful. On the other hand, machine learning for quantum computing is actually a quite mature project or topic which is in use. Yeah, so I'll finish up with that Dilbert comic there, which I think puts the whole thing quite nicely in perspective. So thank you.
Thank you, Mats. Are there any questions from the audience?
Where are the hands?
Some hands.
Is everything super clear?
So before going to this, and as I understand it, a unit vector in 3D as your value, wouldn't it be easier to first go to something like analog computers, which is an old field, not really used much, where you have just one scalar value as your, rather than binary?
Yeah, so instead of rotating your state on this sphere,
Yeah,
I mean,
then you just
would have a sort of an analog amplitude of the. I don't know. That I don't think it's a quantum computer, but
no,
that may be an interesting thing. Yeah. Yeah. I mean, the important thing with the quantum computer is that you're able to rotate on the sphere, so you can actually get complex amplitudes. So they can interfere as waves do. You can get cancellation plus and minus one, or combinations of phases that, when you add them up, give 0.
Yeah.
Okay, we have a question down there.
Do you have any advice on what to read if this doesn't make a lot of sense? Like I know there are books on quantum computers, but there are just too many to choose from if you're like not gonna get a PhD, but still kind of curious.
Yeah, good questions. On the quantum machine learning specifically, or more on quantum computing in general? Actually, yeah.
I mean, you pick, but
yeah. I actually don't have a good recommendation off the top of my head. Sort of an introductory text, right? You don't want a textbook, which is like this.
I mean, I read Scott Aronson's blog. I think that's fine.
Yeah. The blogs.
That's about as far as I've gotten.
Yeah.
All right. Well, if you come to think of one,
I'll send you an email.
Find you.
Yeah.
A good question. That was my question.
Yeah. Well, that's actually a very good question. Yeah. I mean, the quantum machine learning is really so new in a way that it's. I don't know how much is actually popularized in that way. Yeah.
But anyways, it's great that we have this center here in Gothenburg where you work on this.
Yeah.
I think it's super exciting. And just big thanks, Mats, to a great
Right.
report.
Thank you.
And
Thank you.